Just to pick up on the last point I was saying, first of all, hi everybody, the ones who were not basically live with us, and they're going to watch this recording later on. And today is October 15th. We are really at the midpoint of the this semester. This is the 8th week. We still have 8 more to go. So this is basically right. We are in the middle of everything. Uh, Again, the point I was trying to make earlier before the recording was the fact that systems, when they grade Canvas, especially, it's an all or nothing basically option. So I had to go through it, and usually instructors do, especially in the math and physics departments, and even chemistry too. They give you partial credits for basically working part of the problem or getting part of it correctly or things like that. That's why I actually ask that you guys also submit your work to show your work. Now, this exam was kind of a little bit, the midterm was a little bit less than halfway. The second exam, which is going to be the final, is going to be a little bit more material to it. But you guys know now how to work these things. I gave you the review, which is last time was like 27 problems. From that, you ended up with less than half of those problems. So the same thing is going to happen in the final. I'm going to give you a review problems. And that means that you actually go through each and every one of them and try to understand how to work those things. I'm available here for you guys. We have office hours. We have all kinds of time to go through these things. Please shoot me an email. The only requirement I ask for you is do not like send me an email now, tell me can we meet in about half an hour, because sometimes, first of all, I'm teaching other classes and I have probably other things to do at that time, but give me at least 24-hour window so that we can plan things correctly and sit together and work on that problem. The more the merrier. The more people basically come to the office hours, the better, because then we will have contributions from more people to the discussions. So you're given a review exam. I mean, for the exam, you come up with a plan and you say, okay, I have the final probably will have more than that, probably have 40, 45 problems to go through. So I'm going to divide them into this, this, this. The first check is going to go through all of them and decide that, okay, this bunch, I think they're easy for me to do. This is maybe I require a little bit more thinking for me. This definitely, I probably need help with them, trying to make sure I have fully controlled them. Now, make sure the ones that you stated are easy actually are, because you have to go through them too, okay? And then you come up with a second bunch and you go to the last bunch. And sometimes your first impressions are not the accurate ones. What you thought probably is the hardest, maybe with just one trick. Once you got it, it's just a piece of cake, okay? So that's really the plan. Once you go through them, you have to really systematically and do check mark on all of them and you have them fully understood. So that's basically the plan that I suggest for you when it comes to this exams, so that you guys have a way of doing this. Now you come to know me from every single thing assignment that I give you. For those who are sitting in my labs, also they have. Yes, Sharon. I mean, you're welcome to come to the office hours anytime. Ask for them. There is actually there on I'm sorry, on my syllabus. Just let me know that you're coming so that we can basically dedicate the time for it. Now, you have to be warned up front. If it's something personal, of course, I'm not going to record it. I will warn you before starting the recording that I'm going to start recording because I believe what comes next can benefit everybody. So I will record that and basically post it on Canvas for you guys so that you guys can go through it. So I encourage you very much to do that. I really don't want you to be thinking that maybe I'm lost or something like that. That's really not what I want you to do. I want you to take stuff from this class. Okay. Okay. No problem. Today we're probably going, let me see what kind of things I have in mind actually. I have problem. Okay. So let me do 38 then, since this is not problem from page 298. We're going to do that today after we finish the class. And since we are not really, maybe we'll do another one. Okay, we'll see. Okay. So that's the thing that we probably will be doing from now on, in addition to the homework. So Again, we're finishing chapter 15. Last time we didn't actually finish it, so we have to finish that first, and then we move on to the next chapters. We're still dealing with the study of heat, the study of thermodynamics. So that's basically where we are right now. Any other questions before I turn on the PowerPoints? No? Okay, good. So let's go into the PowerPoints and see the remainder of chapter 15. I think according to my notes, this is where we last basically stopped. So here is a question for you guys. Okay, let me see if I can turn on the view again. No, I don't like this view. I'll go back to the normal view. Okay. Anyway, so the same quantity of heat, Q, is added to two different amounts of water. So basically, I have this much. Oh, okay. I have a new pen today. So let me see if that pen can work. So I have the same amount of heat Q, and this is another amount Q. But in here, I have this much water, and here I have less water. Okay. So the question is, the temperature of the smaller amount of water will be what? I mean, this is easy, isn't it? I mean, you can do this experiment at home if you don't believe this answer. Okay. Yeah, if you have equivalent, basically, what do you call them? Burners, similar burners. Okay. Take just half, basically, a pot and another one full it to the brim and see. Okay. You see the first one boils first before the other one does. And although it's the same amount of heat, now what the only difference with them is you have to make sure that they stay for the same amount of time. So if you let them basically sitting for about 10 minutes, you have to allow for the same amount of time for the other one. Now, when you're doing experiments like this one at home, you have to be very careful when you're playing with fire because it can burn. So you have to take all kinds of precautions, just like what you do when you normally go to the kitchen anyway. So it will increase. The smaller amount will get more temperature in it. Okay, the fundamental law that we're working with, and let me stop sharing this thing so that you guys have a mathematical, those who are more mathematically inclined, they can see exactly what we're talking about, okay? So in terms of mathematics, this is the expression that we work with. Let me pick up this color. Let me delete this thing in here. So in terms of the law that we're working with says the following. The amount of heat, which symbol for it is Q, is equal to the mass. That's where the different quantities comes in. It comes into the mass, okay, times the specific heat. This is specific to every single element in this case, every single one. Water has 1 joule per gram per degree. Okay, so that's basically the specific heat of water. So 1 calorie. I'm sorry, 1 calorie. Did I say no? 1 calorie. Okay, so the definition is based on calories times the change in temperature. Okay, so for the one who's mathematically inclined, I have the Q's are the same, the C is the same, both of them are the same, but I have one with more water, the other one with less water. Obviously, the one with less water will have higher delta T, because delta T in this case, the change in temperature, that is going to be proportional to, inversely proportional to the mass. So again, quantity Q divided by C. Those are the same because water is the same, has the same C, and the heat they said specifically is the same. So M is the one that is different. Obviously, the less M, the higher the change in temperature. When you divide by a bigger number, you end up with a smaller quantity. When you divide by a smaller number, you end up with a higher quantity. So this is really the answers most of this prompts in here in this chapter. Okay, a lot of this question rely on this expression. Again, you will have homework problems related to this specific one in here. So you are going to have to work this expression. The mass M, C is given, the difference in temperature, you want to raise the temperature of the water by example, for example, by 40 degrees or 20 degrees, depending on your problem, and the amount of heat you have to furnish to do that. So that's basically the expression that we have. Provided we are in the same phase, we didn't change phases. We didn't go from liquid to solid or solid to liquid to gas or something else. So if we are in the same phase, this expression works beautifully and always gives us the correct answer for how much temperature needs to be increased. If we change phases, there is an amount of heat that needs first of all to go and melt whatever that object is. If it's ice, for example, you want to first melt it before you increase its temperature. Before its temperature rises from zero, and let's say you have a bunch of ice, for example, that was colder than zero. So what you do to it then is you raise its temperature from a temperature, let's say, for example, negative 10 degrees Celsius. Okay, you have to bring it, the ice first. You have to heat up from negative 10 to zero first. It's still ice. Up to that point, it's still ice, but it's being heated up. So you need to dump some heat to it to have its temperature go from negative 10 to zero, and then dump some heat just to convert the ice to water. So for a moment, this expression is not valid. This expression is not going to work because there is no change in temperature. You're going through a phase transition. You're changing from one side to another side. And again, chapter 17, I think, will deal more with phase transitions, but there is a heat during that moment that needs to happen for it to melt. Once it's all melted, then you don't have any ice anymore. Then the extra amount of heat theoretically can go into raising the temperature of the water. So if you have a transition phase change, this expression is not going to work for you. It works only during certain for the entire phase. If it's liquid, liquid. If it's solid, solid. If it's gas, gas. Okay? So that's the only warning for this expression that we have in here. So that's basically in a nutshell for the people who are more mathematically inclined. Like I said, this is the expression we're working with. Obviously, you're going to be dealing with it too. So it doesn't matter if, but that's the thinking. So again, we have the same quantity of heat. Q is the same. The amount of water is different. So the mass is different. Water, water, the C is the same. So the one with the smaller amount of water will see its temperature rise higher. Okay? Because the temperature, the change in temperature is inversely proportional to the mass. Okay? The smaller the mass, the higher the change in temperature. The delta, the symbol delta, and you see it a lot in this class, the symbol delta means change. You can actually read delta and alternatively with change. Okay, that's basically the symbol we use in here. Okay, here is another expression that is following that same rationale. You heat up a half cup of tea and its temperature rise by 4 degrees Celsius. How much will the temperature rise if you add up the same amount of heat to a full cup of tea? Now, the same problem as before. So basically, half a cup, the same amount of heat will give you a rise by 4 degrees. Now, instead of half a cup, you have a full cup. You're not going to get 4 degrees. You're going to get half of that. Okay? You should get only 2 degrees. Do you guys understand the rationale, the mathematics behind it too? Yes or no? Okay, so I think hopefully you guys see the logic behind it, and from now on it should be easy for you guys to decide on these questions. You don't even need to review these things. Okay. Now, if they say, for example, a quarter of the cup. So, for example, you decide to, instead of having half cup, you decide to only have quarter cup, and you put the same heat on it. So basically, you put it on the burner for the same amount of time, because the burner provides power. Actually, it doesn't provide heat. Provide power, which is heat over every second. So if you wait for the same amount of time on the same burner, you're not going to get it at 4 degrees. You're going to go to higher. You're going to go to 8 degrees because now you have less. So if you put a quarter of a cup, now the temperature will double, actually, not 4 degrees, going to start rising even higher. So what you need to know is the following. This is not the actual temperature. This is the change in temperature. Okay? So this is a key word in here. This is not the temperature T itself, but rather it's delta T. So if I look at it right now, it doesn't mean that its temperature is that cold. 4 degrees is very cold, by the way. Means that it actually has increased from whatever it was before by 4 degrees. So if before was, let's say, for example, 25 degrees, now it's 29 degrees. So that's the key thing also. Delta is the change, and that's the key word in here. They say the rises, temperature rises. Okay. Specific heat, and I already mentioned it in the expression, defined as the quantity of heat required to change the temperature of the unit mass of the substance by 1 degree Celsius. Let's go back into that mathematical expression that I showed you to see what that means. I'm going to start sharing the screen and go back into the screen. I wrote that expression in it. This C, what does it mean? That's basically what that is. If I have 1 unit of mass, okay, C, this is 1, whatever it is. I'm sorry, Control Z. That's not the 1 I meant. This is 1 unit of mass, okay? And this change in temperature is also 1. Obviously, C is Q, because if M is 1 times C times 1, the only thing that you're left with on this side is just C, and the other side is Q. I'm sorry, all the way here, it's Q. So that means that C is Q, is the heat needed to raise 1 unit of mass by 1 degree. Okay, that is the specific heat, C. See how this expression helped us also, not just to answer those questions, but also to define what C means. Again, like I said, if you are really, if you can think in terms of that relationship, everything can be explained. So the specific heat, which is C, the symbol for it is the letter C, by the way, okay? Defined as the quantity of heat, Q that is, required to change the temperature of the unit mass. If the unit mass is a kilogram, it's the kilogram, albeit. If the unit mass is a gram, use the gram, okay? Again, that's why the units for it sometimes they differ depending on what you use for it. Of the substance by 1 degree. So delta T is also 1. Like the inertia, like the thermal inertia resistance of a substance to a change of temperature. In other words, the expression that we can go back to, which is still the same expression as before, okay? So let me stop sharing to show you that that answers that too. So if I come to this expression here and rewrite it now, I know it became messy in there. So and rewrite it now as in terms of the change in temperature, delta T itself, this is equal to how much Q I'm going to put divided by M. That is expected. The more matter, the more heat you need to do for it. That's expected. But C is specific to the element. Depends only on what type of material you have to deal with. So this, the higher it is, the lower this delta T is going to be. Because it's in the denominator. The lower it is, the higher this expression is going to be. Okay? So the higher, this one is lower. The lower, the higher the expression. So that means it's like it's resisting on the change of temperature. So if somebody has a high specific heat, its temperature doesn't rise as much for the same amount of heat, versus another one that has a lower specific heat, its temperature rises easily better for the same amount of heat. So if all you can afford, for example, is 1 joule, okay, of heat, or 1 calorie of heat, depending on the unit that you want to use, it doesn't matter. If all you can afford is just 1 of that, and you have 2 materials, one has a higher specific heat than the other, the 1 joule or the 1 calorie will cause lower change in the temperature of the material that has a higher specific heat than this one. This gets hotter quickly. The one with the lower specific heat, its temperature rises quickly versus the one that has a higher specific heat. It turns out water actually has a very high specific heat. In order for you to boil water, you need a lot of heat for you to get it there, which works backward too. In order for it to lose its heat, it takes a longer time for it versus, for example, metal versus a spoon. So if you have your soup, you're cooking your soup, and you have the spoon in, both of them are at that point, they reach equilibrium and they're the same temperature. Take the spoon out and put it aside, its temperature will drastically go to lower, even if you have the same amount of matter, even if the mass of the soup is the same, the mass of the spoon. But the spoon in this case made out of mainly steel, its specific heat is a lot less than that of the water, which means that it's going to lose its heat much easier, much faster than the soup. So that's something that a lot of these questions are really revolving around this property too, for C specifically, not the same, not the mass. Okay. So let's go continue with the discussion. It's the same expression. We use it backward, left, and right, and basically we make arguments based on how it looks like. Share. So, like thermal inertia, resistance of a substance to the change in its temperature, delta T is inversely proportional to C. For the same Q, for the same mass, of course, too, the higher the C, the lower the change in temperature, and vice versa. So different substances have different thermal capacities for storing energy. Takes about 2 minutes to raise the temperature of an iron pot of water boiling to boiling temperature. Takes less than 1 minute to raise the temperature of the same quantity of water in a silver pot to boiling temperature. Okay, that's because the conductivity the specific heat of iron and silver are different. Okay, so if it's the same boiling water, that is not the issue there. But you have to understand it in terms of the expression that I was talking about. Equal masses of different materials require different quantities of heat to change their temperatures by a specific number of degrees. Again, now we're keeping delta T the same. The mass is the same. The only thing is we want to know, we have two different materials. That means they have different specific heats. One with a higher specific heat will require more heat to raise it with the same temperature. So that's basically how it goes. So 1 gram of water requires 1 calorie of energy to raise the temperature by 1 degree Celsius. That definition really works at, specifically between 14.5 and 15.5 degrees Celsius. 1 gram of iron requires an eighth as much energy for the same temperature increases. So if you want to raise, for example, 1 gram of iron by 1 degree, all you need is an eighth, half a quarter of the same heat that is required for water. That's because basically the molecules of water can absorb basically the motion and can move in different ways and take all of that heat before you see actually a kinematic, before you see actually kinetic energy increase, motion, which is the heat, which is temperature, I'm sorry. Okay, specific heat of water plays a major role in terms of the climate on Earth. There is a lot of water, of course, on the surface of the Earth. It's mainly water, as a matter of fact, the entire planet, mostly water, I should say. And because the water in the oceans has a very high specific heat compared to land, water regulates. The oceans regulate the temperature of the lands. If you are closer from the oceans, the temperatures there don't rise that much in the summer and don't drop that much in the winter. And the same cycle happens actually between day and night. During daytime, the temperature for a city near the ocean doesn't rise that much compared to the land, for example, compared to the inner land. And where the temperature rises drastically, there is a big gradient in temperature for the inland versus the places near in the ocean, because again the ocean there plays as a way to basically regulate that, because again its temperature doesn't increase as much and can exchange the heat with the surrounding, to keep it basically moderated more or less. So if the process works that way for during daytime, it's also during the nighttime, the land's temperature will drop drastically, okay, because now it loses all of its heat to the environment because it has a lower specific heat, whereas the ocean and the land next to it, its temperature is regulated by the fact that it's near the oceans. So this plays a major role in terms of climate. And also it tells you how the winds also circulate, okay, because of the way that basically air masses move also in terms of from the oceans to the land and vice versa, okay, depending on the time of the year. Okay, again, this is the question that we were talking about in here. Which has the highest specific heat, water or land? There is a table. I don't know if I shared with you guys or not. I know I shared it with the, the people who are in physics 11, and I know some of you, a lot of you are actually. Let me try to find it, okay? Okay, I'm gonna stop sharing that screen. I'm gonna share with you this screen. This table is straight out from the lab from Physics 11, which is the thermal physics, the last lab we did. So basically what you have in this case, you have the material, and its phase in here, whether it's solid or gas or liquid, and its specific heat, and it's in calories per grams per degree Celsius, okay? Forget about the conductivity for right now. We'll need that next chapter, actually, chapter 16, when we talk about thermal conduction. So, or heat transfer in general. So what you have in this case, you have air. This is a specific heat. Look for the water in here. Water, theoretically, at between 14.5 and 15.5 is 0.99, I mean 1, but this is at room temperature, okay? So it's practically it's 1, okay? 0.99994 is 1, okay? And let's take land. Land is, do we have anything in here? We have wood, soil, okay? Soil is 0.19, okay? So this is the soil, not necessarily land specifically, but I'm just giving you an example in here, which can be representative of land in this case, okay? So that's the soil. So it's 5 times higher for water than that of land. So you need 5 times as much heat to raise the temperature of water versus the same amount of mass for soil by the same degree, basically, by the same number of change in temperature. Whereas if I look for iron, it's 0.10, okay? This is steel, pure steel. Lead, it's even less, okay? Where was the silver? Earlier, we were comparing silver and, do we have silver in here? Aluminum, it has higher specific heat than iron. Here is copper. Copper also is a very good conductor, and its specific heat is very, very low. As a matter of fact, do we have anything in here? Okay, we have concrete, which is 0.2, which is similar to actually a soil. Okay, so these are some of the numbers that give you an idea in here. Out of all of these elements, it looks like water has a very high specific heat. Okay, so that's one of the issues that we're going to raise today for the discussion after. So what we know from this table and what we know from a fact is water in general has a very high specific heat compared to all of the other materials that that are used on a daily basis. Okay, do you guys understand what the answer to the prompt is? Yes? Okay, very good. So you have to be very careful with soup or pizza or that very, very tasty and at least looking very good pie that just comes from the oven because it's mainly water. Okay. So when you bite on it, you have to be very careful. Or potatoes, as a matter of fact. So you have to be very careful with these things when they are just off of the oven or off of the thing. Jeffrey, I think, is this? Yeah, it has a very high specific heat. Water does. Okay. Is that what you're asking, Jeffrey? Because I'm not sure. Okay. So water has a very high specific heat. That's basically the thing in here. Compared, and you can go back to that table and look it up. Okay. It's an unusually very high specific heat, and that's good actually for the people living near it, near the oceans especially. Okay, because you have a large body of water that regulates the temperature in there, and that's why it has an influence over the climate. Okay, so where were we? No, land has less specific heat. Land is mainly soil. Okay, has less than that, about a fifth of that, Kyle. So if, let's say, for example, the sun is dumping on a regular basis 1,000 watts, okay, 1,000 joules per second. That's basically the heat in the middle of the day, about 1,400 joules per second, okay? And I have a body of water. I'm trying to answer the question for Jeffrey in here. And I have the ocean on one side and the land on the other side. And I wait for an hour, okay? That 1,400 joules for every second that I'm receiving from the sun for 1 hour will go to raise the temperature of the land this much because it has a lower specific heat. Meanwhile, the ocean next to it doesn't rise the temperature that much. So there is a gradient in temperature now. This one, the land is higher temperature and the ocean is lower temperature. Now, the air mass next to the lower temperature is sitting at a colder temperature, so it's going to circulate. That's basically because of the difference in pressure in the atmosphere. So because now this is cooler, so the air starts to circulate, taking the heat from the environment and bringing the cool. So it's going to cool. It acts as an AC unit, if you wish. Okay. Does this make sense? Okay, very good. And at night, it's the other way around. Now there is no source of 1,400 joules per second that is coming from the sun on every second. That is. So what happened at that time is the land next to it starts to lose its heat to the air. Its temperature starts to go down rapidly versus the other one, the same thing. It's going to lose its heat, but it has a very high specific heat. So it's not going to lose it that much. So during nighttime, the process reverses. So the land now is sitting at a lower temperature. The air around it is cooler versus the ocean now, which is warmer. So now the air starts to circulate now this way, trying to get its temperature. So again, now the cool air will move to the ocean, and the hot air will come from the ocean to basically regulate the temperature of the land, keeping the land a little bit better, more comfortable than a freezing temperature that drops drastically, like if you happen to live, for example, inland. Okay, do you see how the process works now, you guys? At least in terms of climate.
So basically, if you live like in any beach city, the temperature is just more stable.
Yes, it doesn't change as much as cities, for example, inland. And I can tell you out of experience, I lived in Missouri, and I know. Okay, temperature there changes between summer and summer. It's super hot, much hotter than here, and it's actually there are all kinds of other things also with the atmosphere there. And then during winter time, it's actually super cold. I mean, it's freezing and temperature. I mean, snows and sleet. It's horrendous conditions. Anybody who lived in the Midwest can tell you that. Okay. Does this make sense, though, at least in terms of what we know in terms of specific heats? Okay, very good. So let's continue this discussion. Okay, which has higher specific? Of course, water does. I mean, we looked at the table. We just saw water has higher than anybody. Land is mainly soil, which is 0.2, whereas water is 1, and the units are, in this case, calories per degree per gram. Okay. Now, thermal expansion, that was a subject for the lab for physics 11, basically. Due to a rise in temperature of substance, molecules jiggle faster and move further apart. That's why the substance actually gets longer. Okay, its length changes. Most substances expand when heated and contract when cooled, provided again there is no phase transition. Okay, because if you keep on heating an element, it's going to acquire so much heat that it can change its phase and goes from solid to liquid or something else. Okay, this experiment in here and thermal experiment all talks about solids. So that's why you see in railroad tracks they keep a gap between them. If you have ever ridden a train, at least the older ones, you hear that sound that comes every second, basically every half, probably minute or something, because as the train passes from one portion of the track to a new portion of the track, it goes through a gap. Okay, and that gap is needed because in the summer the tracks they heat and they expand, so you don't want them to buckle. You don't want just one track all the way through and through. Then the problem with it with heat starts to deform. Basically, it starts to go up or sideways, and then the train will have accidents. So you have to have that thing there, and also the same thing that causes also the for the power lines to actually sag also, because if you put them straight tight, and you happen to do that during summer, for example, in the winter they will contract and they will snap. Okay, so you want to do this, you have to be very careful with these things. I think we don't have any phone lines anymore, do we? But at least the power lines, they still do that. So here is the example for the train tracks. Okay, these are lousy engineers in here who worked on this portion. They really need to test their temperature, the region where they are, make sure that everything is fully done. One of its applications, of course, is a thermostat, and we're going to talk about that. You can put two metals, basically, next to one another with different thermal expansion coefficients. Again, the law that you need to use in this case, and that's key, especially for those who did not submit their lab yet, still thinking about it, is, where is my notes here? The change, of course, is in length, that is delta L. Delta L now. So this is in meters, okay? Is proportional to the initial length, L naught, also the change in temperature, delta T. But now every material has its own specific, basically thermal expansion coefficient, which is alpha in this case. Use the Greek letter alpha for it. So again, alpha has the units of 1/degree, okay? And you raise the temperature by so much, depending on the initial length, you're going to have a new length, okay? So alpha delta T is actually the relative change in length. So that's the expression that you have to take into account. So if they're going to build it out of steel, you have to look up the coefficient of expansion. Usually alpha is a very, very small number. It's of the order of 10 to the negative 6 per degree Celsius, okay? That's what the negative 1 in here in the power means. When stringing telephone lines between poles in the summer, it is advisable to allow the lines to sag, because in the winter they're going to contract. Okay, so the change in temperature. So if you put them in the summer, make sure that they sag enough so that the winter at least they don't snap. And the explanation is in there. And that's some trick that people do actually in terms of filling up your gas tank. It's better to do it in the evening than to do it in midday, because the gasoline expands faster. So your tank will look fuller first, and then when you drive it, it's gonna look like you didn't have much. The change is small, okay? Remember the coefficient I gave you? It's still, albeit in the case of liquids, it's higher, but it's very small expansion. I mean, if we're talking about, for example, the distance between power lines, which is typically between 50 to 100 meters, which is a very, very big distance, then that is significant because L naught is big. So all those small change in temperature from, for example, the morning where the temperature is cold in the summer, for example, or in the winter, and then during midday, there is a huge change in temperature in this case for about 20 degrees Celsius. That will be enough for the phenomenon to cause trouble. But if you have a small enough length to begin with, or a small enough quantity of the stuff, so you're not going to see that much expansion to be a problem. And the only reason probably you don't want to go in the middle of the day is probably because it's too hot, that's all. Again, the water has its own unique property when it comes to temperature and here change. So when it goes from liquid to ice, it actually rearranges itself so that the molecules actually are distributed differently so that the hydrogen from one molecule will interact with the oxygen from the other molecule. And in that case, the separation between the different molecules is actually greater than when it's liquid. So liquid water is more dense than ice, and this was actually part of an experiment that was experiment 6, actually, guys, you did for the ice, and that's why the ice floats. That's what causes the trouble for the people on the Titanic, because if the ice sunk, I mean, if the ice sinks, I'm sorry, sunk, I should say, then there would never be a problem with the Titanic. But if that's the case, we have a disaster before our hand. Because if the oceans freeze from the bottom up because of the fact that if the ice happen to have a higher density than water, then of course ice sinks down, and as it does, the temperature from the bottom starts to rise to basically freeze, and the oceans will freeze, and they will never be able to recover. Not only that, but marine life will be impossible. Thing for the reason that the ice basically density is less than that of water, the ponds and the water, at least in the lakes, freezes from the top down, which would allow for marine life to continue to exist. As a matter of fact, the temperature below the surface in the case of ponds and the case of also of as long as the ponds they have a lot of water in them, if they don't have enough water, then they probably will freeze completely. But in case of lakes, they freeze from the top. Underneath that ice, the temperature is actually comfortable 4 degrees Celsius. So it's still very comfortable for the fish to exist there. So this is a very interesting property for water. So again, this is the one I was talking about. So again, the density of the water starts to decrease depending on the temperature. And actually 4 degrees Celsius is where the density is the lowest. And then starts to increase again, okay? Obviously, water is sitting in here and the ice is somewhere in there. So when a sample of 0 degrees Celsius is heated, the first thing it does in this case, it contracts because it's more dense. Okay, as you can see from this curve. Okay, let's do some problems from this chapter first, and then we will see how we can introduce next chapter. I'm going to share with you. Let me first of all go to. So I'm looking at is the even questions that don't have answers in the book, or the odd ones? Which one has the answers in the book? Because I heard earlier even don't have. Okay, I heard that. So I'm going to do 38 since it's even. And let me share with you the question from 38. Trying to copy the text into from, again, since I have access to the publisher's book from their website, I have the entire contents in there. At some point, I was considering to give you to do mastering physics for your class, but I decided not to. Bigger, 20. Okay, so let me share with you the screen. Stop sharing that file. Let's go back into the OneNote. So this is question 38 from the book. Okay, so this theoretically doesn't have an answer on the back. So let's see, which is good and bad. Good in a sense that we can do it, and bad because we may make a mistake and we would never, nobody can check us. So basically at the end, we will be in trouble. So let's try to think about it, okay? But the answer is here. It says the specific heat of steel is 450 joules per kilogram per degree, okay? I don't know what that question mark means. Okay. You see, this is different. I'm using the joules now. I'm not using calories. And the unit that I gave you earlier was in calories, and it was 0 point something in there. You have to remember that 1 calorie is 4.18 joules. So you really have to multiply that by 4.18. And that unit was by grams, not per calorie per gram per degree Celsius. This is per kilogram. So the numbers are higher when they are per kilogram. Okay. Show that the amount of heat needed to raise the temperature of a 10 kilogram piece of steel from 0 degrees Celsius to 100 degrees Celsius is 450,000 joules. This is not water, so don't worry about phase transition. Steel is already solid at 0 degrees Celsius, and it's still solid below 0 degrees Celsius, so it's solid all the way through, and it doesn't melt at 100 degrees Celsius, so it's still solid. Okay, so basically here is the process. You take steel, okay, and you put it in a bucket of ice, okay, and you measure it's basically you raise its temperature now by boiling that ice, basically increasing its temperature from 0 degrees to 100 degrees. So now the ice goes through, basically it has to be sitting at 0 degrees Celsius, not below that. So at 0 degrees Celsius, and you put it under the heat. Zero, starting from 0 exactly, all the way to 100. So we know delta T now is 100. The key that I wanted to make a fuss over is the fact that in this case, delta T itself is 100, and I don't have to worry about phase transition or anything like that because it's solid ice, solid steel. So delta T is equal to 100 minus 0, which is 100. So that is the change in temperature. Okay, we went from 0 to 100. M, okay, can I go down a little bit because this is not, okay. M is equal to 10 kilogram. That's what they gave me in here. Okay. And also C is 450 joules per kilogram per degree Celsius. That is specific heat for this for steel. It's joules per kilogram per degree Celsius also. So that's the numbers that they have given me. They want me to show that the heat needed was 450,000 from the minute we turned on the burner. Okay. Of course, it's power. It's applied every second. Okay. So if I know the rate at which this power is being consumed, I can tell you how long it took too. Okay. So So in this case, the heat for the steel, so I'm going to write it as T in here, is equal to, of course, I just multiply the mass, which is 10 kilogram, times the specific heat, which is 450, times the change in temperature, which is 100. So in this case, if I am careful enough with my calculation, I will have 450,000 joules. Okay, so the answer is 450,000 joules. That's how much energy is needed to raise this steel from that temperature. That's not the only question part, though. The second part of the question is asking, how does this compare with the heat needed to raise the temperature of the same mass of water through the same temperature difference? Okay, so here is the thing. So we have the same mass of water. So we have 10 kilogram of water also. Okay, and needed to raise the temperature of the same of water, the same different temperature difference. So also we want to raise the same mass of water by temperature difference of 100. I have to be very careful with water because we're going to be in phase transition. So when you do this experiment, you have to shut it off immediately before it starts to boil, before it starts to evaporate. Okay. Now we want to know how much heat is needed to do the same thing. Now, before I do the calculation, do you guys, and that's the second question for the day, do you expect this Q for water? That's what we want to find, Q for water, to be higher than or less than 450,000 joules. And I want you guys to tell me now. We found the one for the steel, and we ended up with a number of 450,000 joules. Now they tell us find the heat needed to raise the same mass of water with the same amount of temperature. My question for you guys, do you think I will find the number higher or less than 450,000? It's a guess at this point. And I want you, okay. Kyle thinks it's gonna be higher. Does anybody else agree with Kyle, or Isaac also thinks it's higher? Okay, the second part of the question, why? I agree with you guys, it's gonna be higher. Why do you think so? Very good. So Kyle thinks it's because the water must have a higher specific heat of than steel. Therefore, its heat needed to raise its temperature from 0 to 100 degrees must be higher. Okay. Does anybody else agree with Kyle? Okay. Isaac also second him. Anybody else? V also. Patricia, Samantha. Okay. Let's do it. Let's see if we can get that. Amanda also agrees. Let's see if that's the case. Okay. We said water. Okay, let me change tabs quickly and come back. The C for water, I'm going to use a different pen if you don't mind. The C for water, why it's not allowing me to do that anymore? Grab the other pen. The C for water, remember I said it's 1 calorie per gram per degree Celsius. If I don't have a gram, but rather I have 1,000 grams, which is a kilogram, I have to multiply the number by 1,000. So the C for the water is going to be 1,000 calories per kilogram per degree Celsius. Okay, so just following my rationale in here. Okay, that's one thing. But I need to know what is a calorie in terms of joule. I know from previous slides that 1 calorie is 4.18 joules. Okay, So C of water, to compare apples to apples, since this C was given 450 joules per kilogram per degree Celsius, I need to find the same C for water in the same units. So I have to multiply 1,000 because each calorie is 4.18 joules. So 1,000 of that calories is 4,180 joules. You see the C of the water is 4,180 joules for each kilogram per degree Celsius, okay, for each kilogram. So that's the difference. That's why Kyle and every one of you guys later on thought that because of that specific heat, therefore the Q for water must be higher. Let's plug in the numbers. So the mass is 10 for the water also. The specific heat now is not 450, but rather is 4,180. And the difference in temperature is still 100. Obviously, if I do this calculation correctly, it's going to be 4,180,000 joules. So the heat needed for the water is going to be, let's complete the word in here, 4,180,000 joules, whereas for the steel, it was merely 450,000 joules. So as expected, the heat for the steel is a lot less than the heat needed for the water to raise both of them 10 kilograms masses by an amount of 100 degree difference in temperature. So this example, which is from the book, problem 38, which is going to be part of your homework anyway, okay? And we worked it out together in here. The other problems are going to be 37, and another problem is going to be from, let's do 39, okay? 37, 38, and 39 are the homework for this chapter. Unless, did I assign the homework yet or not? Hold on, I want to check to make sure I don't give you twice as much work for this chapter versus other chapters. Because I want to keep things uniform. No, I did not assign the homework. By the way, the homework is going to be posted during next week because this week is over anyway, and we're supposed to cover chapters 16 and 17 anyway, too. So we're behind a little bit according to the schedule, and that's fine. I don't have a problem with that. So the homework for this chapter is going to be 37, 38, and 39, okay? And one of them, we already did it together. Problem 38, we did it already together. So we answered the question, and this is the one that is even. So we answered the question. So this is going to be part of your review for the final too. So these three problems are included. So from now on, you're thinking, you're going to ask me what is the review for the exam. You know what is coming from chapter 15, at least in terms of review problems. So 37, 38, and 39. And I'm going to post the assignment for next, I'm going to post it next week for this chapter along with 16 and 17 also. But again, we answered a question related to how much heat was needed to raise the temperature of steel from 0 degrees to 100 degrees, which is fine, we can do. And because theoretically this experiment was done on water, okay, we wanted to know how much to raise the same amount of heat for the so here is the situation. If we did this lab in actually lab and we calculated the heat, both of them are taking heat in the same time. If we actually dump the steel inside the 10 kilogram steel inside the 10 kilogram water, which is not, is it possible? The density of water? Yeah, you can, okay? Of course, we're going to do this experiment together. So we're going to turn the burner and we're going to calculate how much heat went to this one and how much heat went to the other one. Now they're bound together, okay? So theoretically, their temperatures were going to allow it to somehow become in equilibrium, and the process will be very slow. So when we turn on the heat, we have to be very careful not to upset the balance between the two elements in here. Otherwise, the temperature of the water probably rises faster, or the steel rises faster, and the other one doesn't catch up with it. So we want them to reach 100 degrees Celsius together. In that case, how much heat was actually coming from the burner? It's the sum of the two. Okay, it's the sum of the two. If we're not careful with it, this can be a problem because one of them's temperature is going to rise faster, and the equilibrium is not there. And this laws only work when the two materials are actually in thermal equilibrium. Okay. Okay. So let's talk. Any question about this problem first before I move on? You guys understand it 100%? The only question for this problem, honestly, is that conversion for the specific heat of water, because the specific heat of water, the table that I gave you previously, has it in actually calories per gram per degree Celsius. So the degree Celsius, we don't worry about it because it's the change in temperature. It's the gram, we need to change it to a kilogram. So we need to multiply 1 by 1,000 to find the 1,000 calories. There is another conversion because the problem that we have before us was in joules, and we have the answer for the specific heat for water in calories. So we needed to find the transition between the two. Typically, if you have a problem like this one, you can ask what is the specific heat of water in joules, not in calories. And you should know, and I already shared this with you guys, that the conversion is 4.18. That's what made Joule actually famous, and that's what the unit for energy was named after him because of his famous experiment. Okay, so you could ask that question later on. But that's really the tricky part for this problem. That was really where the whole thing was. Okay, good. So everything else should be straightforward, and the answer, as everybody expected, was correct. So more heat was needed to raise the temperature of water. And this is the second prompt that we did today, which is namely to answer the question, which one did you predict would have a more temperature, steel or water? We expected water. Why? Because of the specific heat of water is higher than that of steel. And then we ended up with an answer for the steel of 450,000, whereas the water was more than 4 million joules. Okay, so we were correct. Okay, now for the next chapter 16 and 17, let me share with you the screen first, because we still have time technically. I know that we had the habit of finishing stuff a little early because content, but now we really have to at least talk about these things. Okay. Chapter 16 deals with transfer or heat transfer. Okay. Three main processes, okay, for the heat transfer. Conduction, basically, if this were a metal and you heat it from one end, the heat will move through the metal itself and end up on the other side. Okay. So heat from the outside of the house comes to the inside of the house through the walls. Okay. Unless you have very good insulation, heat will come from the walls. Even with the best insulation in the world, you still have heat that comes from outside. You're trying to keep the house cool. In the summer, it's the opposite. Heat is actually escaping to the environment through the walls, even with the best insulations that you can think of. So conduction is a problem or a solution, depending on what you want to do with it. Now, good conductors of electricity like copper and like iron is not really great, but it's a conductor nonetheless. Gold, silver, all of these things are good also conductors of heat because the process is the same. It's through electrons mainly that heat is transferred from one point to the next. Okay, so this is conduction. Convection is the motion of masses of a fluid of some sort, either air or water, for example. Okay, so that says what the convection is. In the case of the sun, for example, most of the heat is actually transferred from the core of the sun, where the nuclear reactions are actually happening, to the surface of the sun before they actually the sun emits the energy everywhere through convection. The gases basically, which is mainly hydrogen and helium, actually circulate in a convection fashion. Some stars don't have that mechanism though. Okay, some stars are too small for that, or they have too high temperature for it, so that they don't go through the convection layer. For the case of the sun, it has actually convection layer. The case of the Earth, for example, between its core and its mantle, there is actually convection, but it takes a long time for it to go through the process. Although it's mainly solid, but it's still, that is how the surface of the Earth is actually transformed on a regular basis. For the case of the oven, it's a big process because you have convection ovens. They use this process where the heat is actually circulated inside the oven from point to point. And again, it uses the concept of density in this case. The air that is sitting above has lower density because it's cooler, and the air immediately next to the burner is sitting at a higher temperature, so it has low density. Having high density will fall. As it falls, its temperature starts to rise. The one that is below now has less density, will go and replace the one that came up, and it cools down. So this is the process of transferring heat from the burner to the top layer of the fluid. That is actually how air masses actually move in the case of climate too. So convection is a major process of transferring heat. So we have conduction, you transfer heat, and convection, you transfer heat. And both of them require material of some sort, a medium of some sort, okay? Whether metals, whether, I mean, there are poor conductors, like for example, wood of heat, but they still conduct, but they are not good conductors. They are actually very good insulators. So there are two types of materials when it comes to heat in terms of conduction: the ones that do conduct and they are actually good conductors, and the ones that don't do well and they are insulators. Okay. So when you go to Home Depot to buy insulating materials, you're looking for those with very low conductivity of heat. Okay. Convection, like I said, requires at least fluid of some sort that can flow. In doing so, it's going to take heat from the source of the heat and basically move it to the point where it can expand of it. So it's a process of actually cooling down. Okay. Now, radiation does not require medium at all. Radiation is how we get most of our heat to Earth from the sun, because the radiation, which is really an electromagnetic phenomenon, electricity and magnetism, once it leaves the sun, it's really in vacuum. There is no gas, there is no fluid, there is no copper to conduct heat. It's a vacuum, pure vacuum. So that is radiation. Radiation obeys a lot of interesting laws in terms of how heat is transferred from location to location. So the main source of heat on Earth is actually from the sun. We have some heat coming from the core of the Earth, but not as much as we get it from the sun. It's the main source of energy, as a matter of fact, and the main process is radiation. So that is how we get most of our heat from in terms of that. So these are the three processes: conduction, convection, and radiation. Okay. Then we talk about Newton's law of cooling. Obviously, if you take a hot cup of water or a hot cup of coffee and you forget to drink it, you put it on the table, and you come back half an hour later, it cools down. It's no good. It's too cold for your taste. So what you do in this case is, here is the trick. If you have a big mug versus a small cup of coffee, the smaller would lose its temperature faster than the other one that is a big mug. So that's really the trick with it. So get a huge quantity and keep it for the entire day. Hopefully you will have enough coffee for you. Same thing. With the warming, it's the opposite too. So if you have a lot of ice, it's going to warm, versus if you have smaller amount of ice, it's going to warm faster. So this is Newton's law of cooling. We're going to talk about the global warming because radiation is associated with heat from the sun. Once there's two different kinds of materials, there is opaque and transparent. And actually, opacity and transparency are frequency dependent. The visible light will come through glass, for example, or through the atmosphere and comes in here and absorbed by the Earth. Once it's absorbed, it's emitted back in the Earth in forms of infrared radiation. Infrared radiation, actually, glass is actually opaque to it. It does not transmit it back. It keeps it there. That's why cars in the summer are very dangerous if you stay them with the windows closed, because the heat is coming. I mean, the radiation are coming through, filtering through the glass. Once they go inside, they're absorbed by the material, and then once they're emitted, the glass does not allow them to leave back. So this bounces them back, and that is the greenhouse effect. And the greenhouse effect is actually an effect used by in the agriculture to basically grow food, but it's actually a damaging thing to basically the entire planet, which is a real deal. Okay, so regardless of what your politics is, this is a real deal. So this is basically what the chapter is all about, okay, in terms of concepts. Phase transformation. Basically, there are three main phases that we know on Earth. They are not the main phases, though, of Earth, namely solids, liquids, and gases. And materials go through phase transformation from one form to the other, depending on which way we're going. If we raise temperature, we're going from solid to liquid to gas. And if we go backward, basically from lower temperatures, we go from gas to the process of condensation to liquid, through the process basically of solidification or freezing to the opposite direction. As I said earlier, when we were discussing chapter 14, there is heat involved with the process of freezing or and the process of also or melting, which is the same process. Backward, you look at it whichever way, or the process of condensation or the process of evaporation, which is the opposite to that. So again, all materials go through that process. There is a fourth phase that we're going to probably briefly talk about, and that is the plasma phase. Plasma phase is actually when the temperature is so high that the material loses its electrons, and that is actually the dominant form of matter in the universe, because all of the most of the mass of the solar system is actually in the sun, and that of also the stellar systems out there. So and the sun and all of the stars are in plasma phase. That's the picture you see behind me is actually a plasma too. That is actually lightning. Okay, so this is a big introduction for the chapters. I know we're going to talk more in detail about them on Tuesday when we meet again. Okay. And we're probably going to skip through stuff there. We're going to hopefully cover the main things. And again, we should have an assignment for chapter 15 and also chapters 16 and 17 next week. Okay. So don't forget your two questions of the day. Does everybody remember them? Yes.
What was the second question?
What was the first question first?
The first one was water has a high specific heat.
Has a very unusually high specific heat, okay, from that table that we saw. The second question was related to the exercise from problem 38 from the book, okay, from chapter 15, where we predicted the steel will have less heat than that of the water, and it turns out to be correct. Okay, and the answer was 450,000 for water for sorry steel versus 4 million 4.2 to be approximate 4.2 million joules for water for the same amount of water and the same amount of difference in temperature. Does this answer your question, Jeffrey? Everybody is.
So we just say that it's hotter.
You have to put some numbers. Okay.
Okay.
Okay. Because there is a prediction and there is an actual calculation. Everybody is happy with this? Questions? Yes? No? Uh, are you guys accessing the to answer a question of Kyle? Do you guys, when you go back, do you see the question? Because I put a lot of comments on your work. No? I think probably I should turn on that feature if it's not visible. Okay, let me check on that because I think that's a feature that I probably need to turn on because I made a lot of comments on those things. And what do you guys?
Do you mean when we like turn in assignments?
Not on the assignments, on the midterm itself. They're asking basically on the questions. When you
Oh,
go back and look at it, let me see if because I made comments in there. Okay.
'cause I can usually see them on the assignments, but I don't think I saw any on the midterm.
Yeah, yeah. I think there is a feature that I need to turn it on the assignments itself so that you guys can see those comments. Okay. Okay, I'm gonna ask one of you guys to be in charge of this, because if you guys don't see it by the end of tomorrow, somebody has to remind me again, because I have a few things also. I have some of you this afternoon and some other things also done tomorrow. So who's gonna volunteer to remind me by sometime tomorrow around, I would say in the afternoon, around 3 or 4 o'clock? Okay. Okay, Kyle is volunteered. So I'll try to do it tonight, if not first thing in the morning. If not, Kyle is gonna remind me to take care of it. Very good. So I'll see you guys Tuesday then. Let me stop the recording first.